Good morning. Today's version of ML Confidential is brought to you by Alex Smoller, Distinguished Scientist and VP at AWS AI. And I'm going to make the case for AutoML. Of course, for that you need some usual suspects. That's the team that did the actual work. I'm just a presenter. So that's Nick, Jonas, Alex, Pedro, Mu, and Hang. And I'm just here to give the presentation. They wrote the actual code. Let's start. So if you look at how a machine learner embarks on a typical machine learning journey, well, they first have to define a problem. And once they've done that, they go and collect some data. For instance, if you want to recognize cats, well, you need to take pictures of cats and take pictures without cats. Or if you want to classify between ham and spam, then, well, you need the appropriate emails and so on. After that, you perform some feature engineering. You transform the data. Maybe you standardize, you normalize them, you map categorical data into one-hot encodings and all of that. And then you ask your friendly statistical modeler, how to build a suitable machine learning model. You go forth and optimize, and then you find out whether it actually worked. And if it didn't, then you keep on doing this again until you're happy with the outcome. And at the end, well, you go forth and deploy. Now, that's fine, but let's actually play the game of have you ever. So not have you ever seen the rain or done something else, but rather have you ever, for instance, used feature embeddings. So why would I care about this? Well, feature engineering is kind of tedious, and in some cases the engineers spent about 70 to 80% of their time just on feature engineering. So any help we can give them is good. And by default, AutoGluon auto-detects everything. Time, date, location, categorical data, real values, user IDs, all of that. And it takes care of a lot of the tedious busy work, such that you don't have to do it. A lot of other AutoML tools don't. But of course, if you know exactly how to embed and how to represent things, well, why should we force you to do what we think is good? You can switch it all off and override it. So we normalize, we remove anomalies, we remove just unique identifiers if they don't make sense. So for instance, in many cases, you might just have a transaction ID in it, and that throws the models off and just makes them monstrous. If you have text, you can use BERT embeddings or ResNest. And you might do that also for more obscure data. Well, for instance, we don't have a good BERT embedding for Klingon, but I'm fairly sure that somebody would feel compelled to do that, maybe for their master's thesis project. And then, maybe you live long and prosper. Okay, sorry, that's on Vulcan, but in any case. So after feature pre-processing, you might build your model, but then how do you know your model's any good? So have you ever used k-fold cross-validation? Well, what is it? Well, you take the data and you separate it into training and validation set. And so in this case, we decided to pick 1/5 of the data for validation. And so I train on 4/5 and validate on the remaining 20%. But there's nothing special about this blue chunk of data that I used for validation. I could use the green chunk or the orange chunk or the yellow or the red one. And all of those 5 choices would be perfectly reasonable. So what k-fold cross-validation does is it takes the data, splits it up into k so-called folds, and then you hold that one piece and you train on the remainder. And what you get with that is much better error estimates. Not only will you get the mean, but you'll also get some variance estimate. Right? And you also can use that for model tuning. Now, then once you're done with it, well, what next? So after all, we spent all the time training those models. And one option is simply you go and throw away everything that you've done. You just remember the parameters which were tuned for a model that was trained on 80% of the data. You now go and use the same parameters on the larger data set, namely the full one, you train it, and then you hope for the best. So one of the issues is, well, does the new model still work? Because after all, your code may have failed on the full data set and may have run just fine before. Your code may have run out of memory. You may have had some numerical instabilities. Who knows? So, but you won't know. You'll just go and deploy, and then you'll find out in practice. So there's a solution to that, and it's called bagging. So how does bagging work? Well, you just go and perform k-fold cross-validation as before, and you get those different models, and then you go and at test time, you actually take an average between the predictions on the various folds to predict the outcome. So this gives you a high degree of certainty about the model because it's the model that you evaluated before, and you can also use it for variance reduction. So to explain in a little bit more math what's going on, you're basically using the validation set to get different variants of the same estimate. So FV is the estimate that I get by leaving out XV among the covariates and YV among the labels. And so I'm basically using 1 over k of the data for validation, k minus 1 over k for training. Okay, so I'm leaving this out. Now, depending on which chunk I leave out, I get different models. And then in the end, all I have to do is I just average over those models. Okay. Now, another nice thing is that we can now decouple two things from another, namely the size of the training and test split and the number of times you train on such folds. So for instance, you might have 20 different ways how you can pick out 1/5 of the data for validation, the rest for training, and then you can average over those 20. This gives you lower variance estimates and thus more confidence. Now, okay, so this is great. If we do that, we'll get a better model. And if you aren't using bagging yet, well, you probably should. So then there's another situation. Namely, have you ever compared your model to k-nearest neighbors? Because after all, we all learned k-nearest neighbors are non-parametric and robust. We also learned that they are usually the punching bag and the laughing stock of machine learning, so they don't work terribly well. Mostly. But occasionally there are cases where they do. And if you're in this situation and k-nearest neighbors work really well and you work better than your model, well, you embarrass yourself by saying, well, I spent several months building a model and then this nearest neighbor classifier beat me. You don't want that. You should probably compare. You should probably also compare your model to a tree. Again, trees are non-parametric and robust and all is great. What's better than one tree? Well, many trees. It's called a forest, and they can be trained in lots of different ways, in random forests and gradient boosted variants, so XGBoost or GBDT and others, and they all will give you some estimate. Right? And so you want to make sure that your model is at least as good as those. Probably you've compared your model to a deep net. But have you used ReLU and drop norm and batch norms and skip connections and all the tricks that offer deep networks in 2020? Maybe, maybe not. The point is, well, you should. And by the way, AutoGluon of course provides that. And so I've made this very long argument about why you should be comparing to a fairly large class of different models. Okay? But why should you just compare, right? after all, what you could do is you could take your own model, you could take trees and forests and boosted versions of them and deep networks, maybe different flavors, nearest neighbors, and use them in combination with your own model. And then you go and optimize the weight of the components. And, well, you just predict using that weighted combination. So in short, what AutoGluon, for instance, provides is you can add your own custom model that you may have built over the past few years with a lot of work, combine it with off-the-shelf networks and trees and other things, and then use the best of all of that to get better results. So we basically take all the busy, tedious work out of it. Now you might ask, why on earth does ensembling work? After all, you just mentioned that all those models are non-parametric. Well, here's one of the reasons. So I might have 3 models, A, B, and C, and they, as you make those models larger, will eventually cover the entire version space. So that's what it's called. But model A has a specific preferred shape and direction, likewise models B and C. And so each of those is going to be great for some problems and not so great for others. But what you can do is, by combining all those models, by taking a convex hull through that weighted linear combination, well, I can get a model that combines the advantages of all of this. Now, I'm not telling you anything particularly new. This has been well known, at the very least, since the Netflix contest, where the throw the kitchen sink at it approach really gave the Belcore team the prize. And to be quite honest, when I first saw this, I was very frustrated because I was looking forward to a very beautiful, clean, logically designed model. And then I was like, oh my God, they've just done everything. They've thrown everything at it. There is no logical structure or system to it. But once you think about it, that's actually the beauty. That they combine multiple models and their strengths to get a good outcome. So if it worked for them, well, why wouldn't it work for you? Well, maybe we're done, maybe not. But actually, there's a lot more to it. If you think about it, well, what I just argued for is, well, it's a linear model of models. And, well, you might frown, like this gentleman on the right. Really, a linear model, is that all you got? So, well, maybe how about a nonlinear model, right? After all, we've learned that nonlinear models tend to be better than linear ones in many cases. So why not a nonlinear combination of models? As a matter of fact, that's to some extent what stacking is. So in stacking, what you do is you take, the original data, the input, and you train the models as I just described. And then you concatenate the input with the outputs of all those models, right? And you use them as new inputs for the next layer of the stack. And you build a new set of models on that. And then you weigh that, and you get a meaningful output. So in other words, the outputs of one layer are the features for the next layer, and you get to reuse features all across the layers. This gives you a nonlinear combination of model outputs, and bagging helps with bias correction. So I'll need to talk a bit about that in a moment. But so if you think about it, what you really get is, input features xi for the first layer, x1i is just xi, and fj of xi for all j. For the second layer, it's, so x2i is x1i, so that's all the features from the previous layer, and so on. And then in the end, well, you can use bagging to reduce the variance. So that looks pretty much just like DenseNet. Except that DenseNet did this end-to-end trained for a deep network. And here it's not quite end-to-end trained because nearest neighbors may not even have a mechanism to train. and you can use that to stack and get a meaningful output. So if you look at that, what really happens is you're using, and this is important, you're using the prediction outcomes that you get by training on the white pieces to predict on the colored pieces. So by leaving out the blue piece, you can predict on the blue bits, and the labels predicted there are independent of the actual labels as the input. So in other words, the predictions and the labels are conditionally independent of each other, obviously conditioned on the covariates. Right? Now this ensures that you're not overfitting, but rather that your features at the next level don't depend on the specific labels. And this allows you to keep on stacking for a few layers without running into any statistical problems. Okay. So now you might ask yourself, have you done all of this, right? Have you done automatic feature preprocessing? Have you used k-fold cross-validation? Have you used bagging, stacking, ensembling? Did you integrate this with other custom models? Did you tune your hyperparameters? Did you do all of those things for your most recent machine learning project? I'm willing to bet that you probably did one or two out of those things, but probably not more than 3 or 4. And why not? Not because you don't know. I mean, after all, these are not any terribly deep insights, but because it's tedious and time consuming and painful. And if you have the choice of solving 2 problems reasonably well or 1 problem in a great way, then depending on the situation, you may choose to solve 2 problems. Okay. And this is exactly where AutoML comes in. So by AutoML, using AutoGluon, for instance, you can automatically do all those things, and you don't have to do any work because we already did all the busy work for you. Okay. So if you've been around in machine learning for a while, you may still remember when people were telling you you should maybe do loop unrolling in C++ or in C. So that's basically, rather than having a for loop for I equals 1 to 10 print I, it may in some cases be faster to write print 1, print 2 up to print 10, right? Now, of course, that makes code horrible. And so very soon people realized that they could automate that through a compiler. Is it always as good as what you would do and could do manually? No. But the difference is you might very well know how to do it manually, but you're in a hurry and then you don't get time to do it. And on top of that, you might forget about it. So in reality, automated code optimization has started to beat hand optimized code, except for a very narrow set of special cases where performance is super critical. But basically by now, nobody writes assembly code anymore. Nobody optimizes like crazy C or C++ code anymore in favor of more readable code, and the assumption that the compiler will do that. In the same way, AutoML can take care of a lot of the tedious busy work and let you focus on the pieces that actually matter. So if you have an existing model, you want to make it better, take that existing model, integrate it with AutoGluon, and you'll get an improvement. Okay, we can actually make the following deal. Do that. If you get an improvement, take all the credit. If you don't, send us data why it didn't work and how it didn't work, and we'll help you make it so. Okay. So why am I so confident? Because after all, if I could be saying a lot of things, but ultimately, the proof of the pudding is in eating it, right? Well, we actually compare to humans. Well, there are multiple ways how we compare to humans. One is we took a bunch of software engineers and we trained them in the dark arts of machine learning, and then we had them in the end build models and try to build something that worked better than an AutoML model. And well, out of 100 engineers, not a single one was able to beat AutoGluon. And you might conclude multiple things from that. You might conclude that AutoGluon is great, but you might also conclude, well, we were just really terrible at training them, or that maybe our engineers are not so good. Well, whatever it is, I don't think it was a problem of the engineers, but maybe they didn't have enough time or whatever. But it illustrates the point that if you need to get something done fairly quickly, AutoML is probably a good tool. Anyway, so what am I showing here? We looked at Kaggle and we took the 10 most popular recent problems and we looked at the distribution over scores. Now, Kaggle has this nice property that if you get things right, or in general, it's a very collaborative environment where the participants actually share models. So in other words, if somebody figures something out, everybody else will figure it out too. Nonetheless, in 2 out of those 10 problems, we're actually in the 99% quantile. In other words, we are 99% better. We're better than 99% of all the other submissions to Kaggle. So the black star, that's AutoGluon. You want to be on the left. And you can see that we win a lot more frequently than others. Mind you, those results are about half a year old. In the meantime, AutoGluon's improved, and I would imagine some of the others have also improved, so the outcomes may be different, but nonetheless, we beat everybody else in almost all cases. Now, okay, well, you might say, well, Kaggle is kind of a special case. Well, how about some more proper AutoML benchmarks, right? So we compared AutoGluon to H2O, AutoML, Teapot, GCP tables, AutoSKLearn, and AutoVeca. And we, again, compared on the, so these are the numbers on the AutoML and Kaggle datasets. And the first thing that we did is we looked at the average rank. So you basically run all the things, you look at where you end up, and you sort them in order, because absolute loss may mean exactly nothing, right? So that's the average loss. It's not terribly helpful. Average rank is a little bit more meaningful. And what you can see is that more often than not, AutoGluon does fairly well relative to everybody else. So it turns out that in 23 of all cases, it's better than everything else. The second thing that you can see is that we don't fail that much. So you might wonder, why would a machine learning implementation fail? Well, exactly because maybe there's something in the data set that's not quite right. So is that the case because we're such awesome engineers and everybody else, including our friends at H2O or Google, don't know what they're doing? No. I believe it's due to the fact that we use a variety of models and a combination of those. And if one of the models doesn't work, well, we still have all the other models that we can rely on. So therefore, we only fail if all the models fail on that data set. This is another reason why you really want to have your nearest neighbor classifier, because nearest neighbor classifiers are insanely robust and it's pretty hard to make them fail. Mind you, the numbers that you're seeing are when we constrain the runtime to be in the order of 200 minutes. I think we constrained it to be under 4 hours, and you can see that all the toolkits essentially stay within that time frame, which is great. But also by allowing for models to fail, you can then spend, your compute time on the rest. So you don't need to try out many times a model that you already know is failing on the data set and hyperparameter tune. So that also allows us to improve the other models where we have a bit more time. Now, if you look at the AutoML benchmark, what we did is we normalized all the errors to 1 for AutoGluon. And so dots to the left mean that something works better. Dots to the right means it works worse. And again, you can see that, well, pretty much everybody works worse than we do, with a small number of exceptions. So, okay, that's great. So maybe we just picked 4 hours because, well, 4 hours is a sweet spot for us and not for others. Well, as a matter of fact, we went and looked at how well the models behave if you compare 4 hours to 1 hour. Well, turns out that in most cases, the 4-hour model, in our case, beats the 1-hour model in a lot more situations than for everybody else. So for instance, if you look at AutoScaleLearn, it's almost a wash. And that means that actually those other AutoML frameworks aren't really able to take that much advantage of extra time. Okay. So to then ask the question, well, I walked you through a whole bunch of tricks. Do they really work? And so we did evaluation studies and we looked at, all the features in AutoGluon, and we looked at the average rank relative to everything else. And so there's basically, as you can see, a significant performance degradation as you go from all the features turned on to cases where you don't repeatedly bag, to when you don't stack, if you use HPO or without HPO, without any bagging, or if you don't use a deep network. And the average rank, of course, is you want to have it as small as you can. And what you can see is that as you turn those features off, stuff gets worse. Each of those improves things by a little bit. In aggregate, you get better performance. So using it is really easy. If you just want to get started with code, you do the following thing. So you need 3 lines of code. You need to import the tabular prediction. That's it. And then you run the fit function. You tell it which data set it is. Everything else is automatic. And don't worry, besides CSV datasets, we can ingest a lot of other things. And you need to tell it which of the columns actually the task is. And then you have it predict. Now that sounds fairly easy, but if you don't even want to write any code at all, well, you can just set it up such that you dump things into an S3 bucket. Then you stand up a Lambda function, so that then triggers automatically, it runs training, and then you can serve the labels straight again into an S3 bucket. So this is zero code AutoML, which is pretty convenient. Now, if you want to try it out yourself, you can do that. For instance, you can just pip install AutoGluon, or you git clone the library and you can modify it. Any of this is fair game. Now, I've just walked you through a lot of the automatic features. Keep in mind, all of those features can be turned off. So AutoGluon is rather different from a lot of the other AutoML libraries. Most of the others simply go and optimize hyperparameters. We try to give you the best model combination. It turns out that mostly model combinations are better than single models. So bagging is great, stacking is even better, distillation is good for speed. So you really should use AutoGluon to get started, and then you can integrate custom models to ensure improvements. So it's a one-stop shop for better models without any need for any extra experience. Now, what you can do is you can download those models. You can go to autogluon.mxnet.io. We have a Slack channel. You can check things out on GitHub. And if you want to read the papers, they can all be found, and they start with Ericsson as the first author. Okay, so thanks for that, and see you next time.